In this lesson, I'm going to be talking about some applications of circular motion. So in the previous two lessons, I talked about the basic maths and the basic physics, the reasoning behind how circular motion occurs. And I'm now going to apply that to real-world scenarios. So the first scenario I want to talk about is a car around a bend. In other words, a corner. So a car going around a bend, going on a corner. If I draw a road here, and there's a car, will experience a centripetal force, okay, F sub C, and that's due to friction, as I mentioned before, friction between the car's tires and the road, the surface, okay, and it acts towards the center of the turn. All right, so there's a centripetal force acting towards the center, and greater friction equals greater centripetal force. Right, and drivers or passengers, they experience this outward pulling sensation due to inertia. Right, so the car wants to continue in a straight line according to Newton's first law, but doesn't do so because of the centripetal force. Right, it's got to be turning. It's turning, and so therefore there's a force that's sort of pulling it inwards at the same time. And if you recall, the centripetal force, F sub C, is just mv squared over r. It's just the mass of the object, which in this case is the car and the occupants, times the velocity squared of the car, divided by the radius r of the turn itself. Let's see how this works by looking at an example. So suppose you have a circular radius, circular turn of radius equal to 20 meters. And suppose the coefficient of static friction is 0.6 between the car's tires and the road. So I'm writing shorthand here just to save time and space. What's the max speed at which the car can safely turn without sliding? So we need to work out the max speed. How do we do this? Well, the first thing to do is to really picture what's happening. So let's draw a car. Let's draw a road. What are the forces acting on the car? Well, we know what that the car has a weight force acting downwards. Okay, F sub W, weight force, and that's equal to just the mass of the car multiplied by gravity. There's also a normal force acting upwards, F sub N, which is just, once again, the mass times gravity. And there's also a centripetal force acting on the car. Let's take the frictional force. So the frictional force, F sub F, is just, if you recall back from year 11 preliminary physics dynamics, the frictional force is just this coefficient of static friction times the normal force in this case, because we're dealing with static friction in the problem that we're given. And that opposes, I should say, the centripetal force F sub F. So let's set these two things equal, the frictional force and the centripetal force. So all I've done is just equate them. Now we need to get rid of some of these terms here because we're not actually given them in the problem. In this case, the F sub N. So let's divide the left-hand side by F sub N. Okay, because we're not actually given the mass of the car, right? And similarly, the right-hand side, let's divide that by mg. Right, so F sub N is just mg, if you recall. Right, the normal force is equal to the weight force. So we can do this mathematically. Okay, we haven't changed anything. All we've done is really divide both sides by mg. Right. So the F sub N cancels out on the left-hand side, and the m's cancel out on the right-hand side. So what are we left with? We're left with this. We're left with, if you rearrange this for mu sub s, the coefficient of static friction, mu sub s is just equal to v squared over rg. And so rearranging this for v, let's call the v sub max. That's the max speed that we need to work out. If you rearrange this algebraically, you'll find that v sub max is equal to the square root of r, which is the radius of the turn, which is 20. Actually, let me just put in the symbols first. R times gravity, g, times the coefficient of static friction, mu sub s, and then putting in the numbers. R is just 20 in the question. Gravity will take it to be 9.8. Coefficient of static friction of the question is 0.6, and that's roughly 117.6 meters per second. Okay, that's the speed. That's the max speed that the car can turn safely without sliding. So that's the first application of circular motion. Let's now look at another application. Circular motion on a frictionless banked surface. In other words, on a slope, an incline. So suppose you have a car once again on a banked, on a slope, on a road, with some angle of inclination theta, and it's experiencing a centripetal force once again towards the center of motion, okay, at some radius r. Let's figure out what's happening in this case in terms of circular motion. Well, let's draw a free body diagram to look at the forces acting on this car. Okay, so angle theta. Let's just have a dot here representing the car. So remember, free body diagram just shows the forces acting on an object, with the object represented by like a dot or a circle or a square. So the first force we can that comes to mind is the weight force, F sub W, which is just mg, acting on the car. And the normal force should be drawn like this, F sub n. Just draw a right angle here. Now, let's work out the components of the normal force. Remember, the normal force in this case, because it's a banked surface, it's not going to be going straight up, right? It's going to be coming out at an angle. So this angle here, I'll draw an imaginary line here, a normal. This angle here is theta. Why do we know this? Well, because if I draw another line here, horizontal line, this angle here would just be 90 degrees minus theta. All right, and this angle here is theta. Because this angle here and this angle here, they're alternate angles, okay, z angles. If you recall back from basic maths, they're alternate. And so therefore, because this angle here is 90 degrees, okay, this angle will therefore be theta right there. And so the component of the normal force will just be F sub n cos theta for the vertical. For the horizontal, it'll be F sub n sine theta, okay, because that's a right angle triangle here. And so using this picture, we can basically work out angles. So cos theta, what's cos theta for this triangle here? Let me just use a highlighter quickly. This triangle here, cos theta. Cos theta, so cos is just adjacent over hypotenuse. The adjacent is just Fn cos theta, right? F sub n cos theta. The hypotenuse, which is this thing here, this line there, this line over here, is just the normal force. And similarly, we can work out, so that's cos theta. Now the centripetal force, that's a result of the horizontal component of the normal force, Fn sine theta, as you can see up here, right? It makes sense. So that's equal to F sub n sine theta, which is just mb squared over r. And the normal force itself, F sub n, depends on gravity. Right, so F sub n cos theta will be equal to mg in this case. Okay, if you look here at the diagram, this thing and this thing, these two lines are equal, right? So now let's use these expressions. Let's call this expression 1, and let's call this expression 2. Let's play around with them, see what we get. Let's divide expression 1 by expression 2. So let's do 1 divided by 2. So we get n sine theta, f sub n I should say, sine theta divided by f sub n cos theta. Now, f sub n sine theta is just mv squared over r, and f sub n cos theta is just mg. And mathematically, when you work this out, you get that v squared is just rg tan theta, right? Because these two cancel out, and sine divided by cos, if you recall from basic maths, is just tan theta. Right, so tan theta is equal to this thing here, m's cancel out. Rearrange, you get this. So therefore, v is the square root of rg tan theta. And this expression can tell you a lot of things. It can tell you, for example, that increasing the angle of the banked surface, the angle of inclination, if you increase theta, that'll result in a greater tangential velocity v. Right, also, if you increase the radius of the circular motion, you'll also have to increase the tangential velocity v. So let's do an example to see how this thing works. Okay, so let's suppose a car makes a circular turn of radius 50 meters going at 40 meters per second. What angle should the road be banked so no friction is needed? Looks a bit complex, but let's just break it down bit by bit. It'll make more sense. So we'll draw a diagram once again. Let's draw an inclined road at an angle of theta. Free body diagram. Here's the car. It's got a weight force of mg acting down. It's got a normal force coming out like this. Okay, this is angle theta, and we know from before that this is the vertical component of the normal force is just f sub n cos theta, and the horizontal component of the normal force is just f sub n sine theta. Okay, just a picture of what's happening. So let's use what we used before. We know the centripetal force is just equal to the horizontal component of the normal force, which is just f sub n sine theta. That's mv squared over r. And we know that the vertical component of the normal force is just f sub n cos theta. That's equal to the weight force mg. So we've got two expressions here. Let's do what we did before. Let's divide the first expression by the second. So we'll get f sub n sine theta divided by f sub n cos theta. And that's equal to mv squared over r divided by mg. I'm not going to go through this again because what we had before was just this, if you recall. Dot, dot, dot. We just had this. We had v squared is equal to rg tan theta. Now we want to work out what the angle should be in order for the road to, in order for the car to experience no friction. So let's rearrange for theta. So tan theta is just v squared over rg. To get theta by itself, if you recall from maths, if you have tan theta, to get theta, you just take the inverse of tan, v squared over rg. So we've done the hard part. The easy part is just putting in the numbers now. It's equal to the inverse tan of v squared. So v in the question was just 40 meters per second. So 40 squared divided by r. R, the radius of the turn, is just 50 meters, 50. And g is just gravity times 9.8. And that is roughly, to two decimal places, 72.97 degrees.